Hi everyone, this is Professor Chia, and I wanted to quickly um, do a review on the use of QM as well as Excel, because I had 3 students ask to get to know a bit more about how do we use QM and how do we use Excel in calculating all the different problems that you're required to calculate for this course. So I wanted to start off by looking at a quick example that I'd like us to review in both Excel and QM. And hopefully this will give you a better understanding of what you need to do to be able to answer most of the questions that you'll be doing. If you're asked for a question to be solved in QM or in Excel, you should be able to be confident doing this. So I'm going to start off by reviewing question 7 in chapter 3 of your textbook. And I'll start off by doing this in Excel and then go into a discussion of the same question in POM QM. Okay, so the question that I have here reads: a company produces 2 products, A and B, which have profits of $9 and $7 respectively. Each unit of product requires 2 resources as follows. So the resource 1 and resource 2, and we're told how much of each product takes. Okay, and then we're given that each resource has a maximum. In the case of resource 1, the maximum amount of resource available is 60, and the maximum amount of resource 2 available is 40. Okay, and just so that this becomes slightly more clear, let's use an example here where we're talking of a company that manufactures chairs. Okay, and but manufactures both chairs and tables. So let's assume that our product A is chairs and our product B is tables. Okay, and let's assume that our resource 1 is time in hours available to the organization, and our resource 2 is labor, the number of employees available to manufacture a given product. Okay, so this basically tells us that our resource maximum amount of hours available to the organization will be 60. The maximum number of laborers available will be 40. Okay, and with these resources, we want to try and figure out what's an optimal solution to the question that we have here. So the first question that we have here says, formulate a linear programming model to determine the optimal product mix that will maximize profits. So when you're asked to formulate a linear programming model, this is basically asking you to write down in notation what it is that you're trying to achieve with this whole linear programming model. So in this case here, I see the word profit. And that to me should automatically indicate that this is a maximization problem. It's very rare that you're going to have a profit question that asks you to minimize profit. It doesn't make sense in business. You always want to maximize profits. On the other hand, if you see a cost question, chances are the question is asking you to minimize costs. Okay, so always when you're trying to write down your model, ask yourself, what is it that you're trying to do? Okay, so in this case here, we are trying to maximize our profits. And how do we maximize profits? By selling as many units as we can, given the different resource constraints that we have available. So I know that our profit, let me take this, it's confusing here. Our profit for each share will be $9 and our profit for each table will be $7. So if I want to figure out what my total profit is going to be, it's going to be $9 per chair multiplied by however many number of chairs we end up making, plus the $7 per table multiplied by however many number of tables we end up making. Okay, so objective function then becomes this, but I want to write this in a manner that makes algebraic sense. So I'm going to change this maximum profit. Let's change this word profit to the letter Z. It could be any letter you choose. The book uses Z, so let's use the book's notation. Maximize profits by maximizing your 9x. Let's use the notation x1 for chairs plus 7x2. Okay, so that's our objective function, and that's what we seek to achieve throughout this whole process, objective function. And the next thing that we want to know is what are our constraints, because our ability to maximize profit is subject to our constraints. So what's our first constraint? Our first constraint has to do with resource one. We have a total of 60 hours available, and so we're going to write this as follows. For resource one, chairs would take up 12 x1 plus 4 x2, and this is going to be less than or equal to 60. And let me just explain what that means. Okay, 12x1 is basically telling us that each chair is going to take 12 units of that specific resource, and we're going to multiply it by however many chairs we make. That's the x1. We don't know what that is. It's a variable. We have to let our system figure out what that x1 is. Okay, plus 4, which is the number of hours it takes to make a table, multiplied by the number of tables we eventually end up making. So we don't know what that x2 is. We leave it as a variable as x2. We have a second constraint that I see here. The second constraint has to do with our labor. Okay, so it takes 4 hours to make a chair. Sorry, 4 laborers to make a chair, multiplied by however many number of chairs, which is x1. We don't know what that is just yet. Plus 8 laborers multiplied by x2, the total number of tables made. And this is limited to a maximum of 40. Okay, so we can only use as much as 40 units of that specific resource. Okay, we have a maximum of 60 hours here, maximum of 40 laborers there. We cannot go above what we have. Okay, the last constraint that we have is called our non negativity constraint, and I'll write it down and explain it. x2 greater than or equals to 0. Okay, and what this tells me is that basically we cannot have a negative variable. Okay, we don't have negative hours available to us. We don't have negative laborers. Okay, we don't have a negative human being. So at a minimum we'll make 0 chairs, 0 tables, but beyond that we can make as however many as possible based on the different constraints that we have. Okay, so this right here becomes our linear programming model. Okay, and that answers our first part of the question. Next, we want to solve this in a manner that enables us to calculate what's the maximum profit going to be. Okay, and so I'm going to take what I have here in my model and the information I have here and turn this into an Excel-based linear programming problem. Okay, so to do that, I'm going to add, I don't have this on here, so I'm going to add a cell here where I'm going to calculate my maximized profits. Okay, so in order for me to maximize my profit, let me use a different color here. For me to maximize my profit, I need to have my x1 and x2 somewhere. So let's say this is our x1 and x2. I don't know what these are going to be, but I'm going to have solver try and figure out how many tables and how many chairs should we make. Okay, so I'll leave this blank for now. We just assume that these are decision variables. And the decision variables, because they're basically the decision here is how many chairs, how many tables should we manufacture. Okay, now we need to know these two. We need to know what's our objective function, but we also need to list down our constraints. So typically what we would do, and I'm going to go ahead and do it here, I'm going to list my constraints horizontally. So I'm going to list my resource 1 constraints, and then our resource 2 constraints. So basically, I'm going to take what I have here, plug it here. So I have a 12, 4, and let's have this less than or equal to 60. And then I have 4, 8, less than or equal to 40. Okay. And I'm also going to put here my objective function. So my objective, my parameters are $9 for profit for the chairs, $7 of profit for the tables. Put this into dollar signs. So I'm just, what I'm doing here is basically building a table that I can then go into Solver and solve. Okay. Now, what I want to have done with my constraint here is that whatever value I'm going to have plugged in here should be less than or equals to what I have here. So let me highlight these two cells here. I want to plug in some formulas here, which once I calculate them will enable me to have a value that's less than 60 and have a value that's less than 40. Okay. And how do I go about doing that? I go back to my model here. So I had 12x1 plus 4x2 is less than or equals to 60. So let's go ahead and do that. So 12 times x1 plus 4 times x2 should be less than or equals to 60. Currently, that'll show that pound value because I have letters here, but I'll delete that. Let's take this out, and then I'll do the same for the second resource, and this will equal 4 multiplied by however many number of chairs we make, plus 8 multiplied by however many number of tables we make. And so at the moment, we've not yet optimized this. We're going to let Solver do that for us. The last thing that I'm going to do is put a formula for my objective function, and that will be this formula right here, 9 times x1 plus 7 times x2. So for my objective here, I'm going to have 9 times x1 plus 7 times x2. Okay. So we have formulas. Let me put this in green just so that we see that that's a formula box. And the only thing that Solver has to plug in for us is to tell us how many, based on our constraints, how many chairs and tables should we make. And that's what we have in orange. Okay, so I'm going to go into Data, Solver, and first thing we do is set our objective. In this case here, our objective is to maximize our profits. Make sure that this is set to maximize. If it was a minimize function, we'd do a minimize, but in this case, the maximize. By changing our variable cells, these are our decision variables. Our decision variable cells, just highlight those. And the second to last thing I do is add our constraints. So my constraints here is that our resource, the maximum amount that we're going to use of resource 1 should be less than or equals to 60. Then I'll add the maximum amount of resource 2 that we're going to use should be less than or equals to 40. Okay. Then if you go back to our model here, we had the non negativity constraints here. And I'm going to do that by checking on this box right here, and then making sure that I'm using the simplex LP approach. Always use a simplex LP approach for all problems that you'd be doing in this course. Okay, and then you solve. Okay, and once we do that, we get our optimized solution, which tells us that given the information that we have here, our maximum profit that we're going to make is $57. Okay, so that's the approach that we would use in Excel. One last thing that you might want to throw in there is a sensitivity analysis. And to do that, you have to go back into Solver, click Solve, and click on the sensitivity analysis, and just click OK. and that will bring up a sensitivity report similar to what we have here. There'll be a new tab that is generated on your spreadsheet with your sensitivity analysis report right there. And where were we? Disappeared. Okay, that's weird. Okay, there we are. Okay, so that's how you go about doing this in Excel. The other option, in situations where you're told to graph this, you'd go into POM, QM, and let me type POM. Hopefully by now you have the software downloaded to your computer. And once you're on QM, look for linear programming. There are different programs available here. What we're interested in is the linear programming problem. Make sure you know the number of constraints that you have in your model, excluding the non-negativity constraint. So we had 2 constraints and 2 variables. The variables are the x1 and the x2. Click OK. And then it basically asks you to then put all that you have here into these cells right here. So we're going to maximize 9x1 plus 7x2, subject to the first constraint, which was 12 and 4, should be less than or equals to 60. Second constraint we have here is 4 and 8, less than or equals to 40. On QM, you don't have to add the non-negativity constraint. It's going to do it automatically. Just hit solve. And it'll give you a solution here, 57, as your optimal maximized profits. But because this was a graphing problem, you'd go to the bottom of your screen and look for the tab that's titled Graph, and it'll give you a graph. Okay, and on the side of the graph, it will give you again your optimized solution here. It will be highlighted slightly different from the other number that you have. Okay, and so you'd copy this by right-click and copy an image, and you can just go ahead and paste this into Excel. Okay, and that then will be the fast way to go about answering this type of question. Okay, so hopefully this helps with QM. There are multiple functions that you could look at. There are actually a couple of things that we're going to be doing that you can do in QM pretty quickly. I usually don't encourage you to use a QM. I'd rather you use Excel, because when you get out of the academic workspace and into corporate, you're going to be using Excel more than you'd be using QM, which is more academic. Okay, but it's a great tool, especially when you want to graph a given linear programming problem. Okay. All right, so I'll end this video here, and I'll pick up on another topic next time.